all of what this means as we go through it. And this work was thanks to my amazing advisor at UNLV, Dr. Colbreth. He is the one who, when I said in the end of my undergraduate, this is cool to gas dynamics, he says, but you know what's cooler? Nuclear rockets. And just led down this huge tangent of my life. It's been fun. So first thing we can talk about is the anatomy of a nuclear thermal propulsion rocket. The most important features that we can talk about are basically that you start with a cryogenic coolant that will ultimately go through a bunch of systems that you can see on the left diagram, and then through the reactor where they will heat up and be expelled as a propellant. So it's actually a dual feature. The propellant that we tend to use is hydrogen, because although everybody loves to just kind of keep it cryogenic, so we don't have a ton of really high temperature properties, what we do know is that its low atomic mass allows for the optimal thrust in this configuration. So this allows it to get to the highest, fastest, strongest option we can get. And that's our goal. That is the goal of the NTPs in order to compete with the chemical rockets. And logically, first thing, I know a lot of people have some very real reservations about nuclear propulsion. I would like to note that there is no mission that would ever launch a nuclear rocket. The goal tends to be to assemble them in a low Earth orbit setting, like on the ISS, where pieces of them were launched separately to avoid any potential for any problems with it. And then it's actually a transit vehicle between various locations, various celestial bodies. A couple of asteroids have been primary targets for ideal missions, but Mars is obviously on the docket there. The moon is actually pretty close for what this goal is. This is more of that intermediate range.
Excuse me, Valerie,
Yes.
two of the attendees indicate, I think your preview screen is showing up. Is it possible to focus just the main presentation?
I'm sorry, what's the problem?
The preview for your presentation, they are seeing two parts. One is on the left is the main screen, but on the right, oh yeah, now it's good.
Great, thank you.
Thank you
So much for letting me know. Yes, so the process of this is we have our liquid hydrogen tanks that just go with the rocket when it's launching, and they sort of diverge into two separate streams. One will cool the nozzle, in which it'll vaporize, and the other will cool an element called the tide tubes, which I'll get to in a minute. And those, after that, the flow will be vapor, go through a few more channels, but ultimately end up going through the core, which you can see in the right diagram is that center bit there that's actually pretty skinny. And as it heats up there, it enters at about 100 Kelvin and leaves at about 2500 Kelvin. Goes through a Laval nozzle, and then you have some pretty exceptional thrust. Some of the original studies of this particular design, this is called the Small Nuclear Reactor Engine, or SNRE, developed by Glenn Research Center. They found that the specific impulse can reach about 941 seconds in their paper study. So we still have to consider what the experiment would look like, but this is all based on some very old experiments, significantly older than me, like started in the 1950s, the NERVA and ROVR projects. They actually got to do experiments on this stuff. We have amazing information from it, and I've always loved seeing it. It was unfortunately cut before we got to do some really good smaller level what if we changed little pieces experiments, but they found that we could do some pretty exceptional things with this. And this reactor is a modernized version of the smallest reactor they tested that was surprisingly successful, called Pee-wee. It was very cute, especially the name. So in talking about the bimodality, one of the things that we like to do with the advanced reactors is figure out novel ways to improve them, because everyone can think of a reactor. This is just a reactor. What do we do with it? But we have to think of the way to remove the heat. And I love thermal engineering, so I loved this side of it. And heat pipes are a pretty magical way to do it. They are a passive and isothermal heat exchanger, completely enclosed. They're just their own control volume. You add heat to one side, it vaporizes the fluid, moves to its far side where you have a heat sink. It condenses there and it travels back in a concentric flow, as you can see in the left diagram. Those regions are named, so when this is put in a reactor, that evaporator section is contained entirely within the reactor because that's all the heat addition section. That's how the evaporator is defined. Similarly, the adiabatic region is defined as no heat transfer at all. It is purely a transfer mechanism, and the condenser section is wherever heat is removed. So that would be wherever the power supply or the power conversion unit would be outside of the reactor. So talking about some pieces inside these nuclear rockets, and I've taken these to a lot of conferences. They're very fun. We've got some visual aids. This is the size of a fuel element. This is against me. So it's actually very, very small, but it has 19 little channels in it. You can see it on the left diagram. And these are where the hydrogen flows through. If you have studied a lot of friction, you'll know that there's a lot of friction because these go very, very fast at very, very high temperatures, and hydrogen has a tendency to want to disrupt things when it is very fast and very high temperature. But these are, in the design that I'm referring to, made out of a really cool matrix that I'll go a little bit more into detail because I have a good image of, but it is made of uranium carbide, zirconium carbide, all contained in graphite, and it's proven to be pretty effective. These all have very specific parameters, but essentially the reactor itself just has a bunch of hexagonal elements that hold together very nicely. And the same size but different inside there is a tie tube, which is the very pivotal thing of my talk here. It has 6 concentric cylinders containing Inconel structural elements to hold the reactor together, as well as a flow channel that will go down and back up each element, and that's one of the early flow pieces where it's vaporized. And then that flow is used to power the turbo pumps that then push the rest of the flow through. It also has something very important, a moderator. And a moderator, for those who don't know nuclear engineering, is something that allows the high energy particles to be slowed down a bit, which allows for the chance of a nuclear reaction to be increased. And so it's very ideal when we want a more controlled reaction. And this is how they fit together in that right diagram. The tie tubes generally are surrounded by 6 fuel elements, and they just kind of keep doing that. So you'll see about tie tube, tie tube, tie tube. And the reason I have investigated coatings and whatnot is because of a noted problem in those early experiments, a substantial mass loss along these channels. Now, a fuel element itself is not this long. It is significantly longer. It's about 1 meter. And there are hundreds of these in any given reactor. The problem is that because of this hydrogen, because of how high temperature it is and how volatile that hydrogen can be, it actually ate away at this matrix. And so they noticed this substantial mass loss. And that is not only a problem because this is nuclear material, but it also means that our reusable model of this is completely limited. To have to replace the fuel elements kind of defeats the purpose in many ways. So what they ended up doing was trying to experiment with options to try and fix it. The first one is they actually changed up the fuel element itself. Originally, they had taken the uranium particles and coated them in carbon, and then that was within a graphite solution. Then they did this composite matrix in which it's a little bit more distributed and they can get a little bit more of other things like the zirconium carbide, and that really helped. They also ultimately added these coatings. They tried zirconium carbide and niobium carbide. Niobium was first, and it had this benefit of being substantially higher than that maximum operating temperature, which these can reach 3000 Kelvin. So generally, when you're trying to decide what to do with any other material, it can't melt below 3000 Kelvin. So niobium was great. It was plenty above that. However, it didn't really bond to the fuel elements, and it just didn't do very well compared to their next attempt, zirconium carbide, which bonded exceptionally well and actually helped reduce it. We can see from here, where on the bottom graph, the niobium carbide is the blue, where you still had some. The green is the zirconium, and the red is that composite matrix. They also found that the coefficient of thermal expansion was a huge, huge factor in this. That because the coating had about a 7.6 compared to the fuel elements at a 6. That was why we were seeing some micro cracking, because the location where these serious mass losses occurred, which is called the midband region, actually coincides with the temperature range in which the coating is applied. So what they ended up doing is finding that if they increased the carbon content in the fuel elements and made sure that they had a coating that had a closer coefficient of thermal expansion, and then ultimately included zirconium carbide in the fuel elements matrix, they were able to more closely match those coefficients of thermal expansion, and the cracks were drastically reduced. You still had a fair bit at that peak region there, but it was enough that you knew you were in the right direction. And it was at this point they had discovered these things. They even had new fuel elements with new coatings and everything manufactured when the funding stopped for these experiments, which was very unfortunate. I have searched far and wide to find out what those things were. Nobody knows. So we did a paper study. First, I made an MCMP model, and MCMP is the Monte Carlo N particle transport code, which is basically a neutronics code and is kind of difficult but pretty popular once you can get it working. It's very robust. And all of these green ones in here are individual tie tubes, and the pink and purple are just badly rendered fuel elements. That is how many there are. Around so this main part here is the reactor itself, but surrounding it are various other safety mechanisms and control mechanisms. My favorite being the tan and green are called control drums. The tan part is beryllium, which is a moderator, like I said, slows down neutrons and allows them to be absorbed better, and it'll increase the nuclear reaction. The green is a poison, which will absorb those neutrons that allow the nuclear reaction to occur and therefore inhibit it. So when these are turned, which that's kind of their main feature, they can increase or decrease the nuclear reaction, and that will control the power. It's very cool. So we developed this model to try and assess what some different coatings that weren't necessarily tested would potentially do to the reactor system. We also wanted to look at a number of other things, but this is kind of a big feature of this, and it also shows what the reactor looks like. But in this particular case, we simply wanted to see what different coatings would look like, so we changed nothing else. This isn't a design study, just a test of what different coatings might do compared to others. The model itself, and this will describe what the reactor is like. You can see that the blue are the individual coolant channels. The pink here are the fuel itself, so they're the graphite matrix. And this very multicolored hexagon, that is the tie tube. It has all those pieces. It's very fun. This is, in particular, it's a very specific model that NASA's Glenn Research Center developed. Lots of parameters. Essentially, if you're interested, feel free to look, but they can be next to meaningless unless you're trying to do it yourself. I found that out. Basically, this one is a slightly lower specific impulse than one of their other models, but it's one that is commonly used because it is a nice size. And in addition, the bimodal option, I'm going to talk about that really quick. The bimodal option is one in which not only does it generate thrust, but also electricity. How I did that was, instead of those tie tubes, I replaced them with heat pipes. And I'll go into a little more detail on the motivation of that and what impact it has. But essentially, the goal was to have two separate loops that could operate simultaneously so that the hydrogen going through the fuel elements would generate propulsion, and the heat pipes could take any extra heat and use that to convert to electricity for onboard systems or whatever one would need. It'd also be very useful for startup, in which you kind of have to give it a little kickstart, but it's not going to be hot enough for the propellant to be a propellant. It more functions like a coolant, so you lose some hydrogen. It'd be very good to make startup easier. Yes. These are all the different coatings we looked at. It was many. We tried to do carbides, nitrides, and hydrides. The carbides are common, they have a lot of information, and they fit well with graphite. The nitrides and hydrides, though, have this benefit of being a little friendlier with hydrogen, but even more importantly, are moderators. So we would have a better sustained nuclear reaction, especially in the case of adding in heat pipes. When we'd be taking out a huge moderator element, we need to replace something somewhere. We also looked at different variations of the control drums. The maximum reactivity tells us what is the most reactive this rocket could be. The 180, the minimum, tells us, all right, what is it basically powered off? And then for the bimodality, this is actually the order of changes. First, we replaced the tie tubes with heat pipes. Then we introduced a few other features to try and perfect it. In order to evaluate how good these coatings were, I and my advisor developed a parameter that would allow us to have a number that we could compare. Now, it has no weighting of which given characteristic is the most important thing. But we have melting temperature. Now, that's more of a threshold. If it's below the 3000, it's basically not going to work. But the higher it is, the bigger factor of safety you have. The thermal conductivity, obviously, we need that heat transfer. That is one of the actual limitations of this particular reactor, isn't how much heat is produced, but how much heat we can remove effectively. And then the thermal expansion coefficient compared to the fuel's thermal expansion coefficient. So that difference is very important to us. That coating's nuclear reaction rate, basically we don't want a coating to reduce it. There are some coatings that will act as poison and actually reduce a nuclear reaction, which kind of defeats the purpose of their use in a nuclear reactor. But also the hydrogen diffusion coefficient. Now, this is not a common parameter because it's purely experimental and it's based on a lot of things, but it is between the two materials. For example, hydrogen going through zirconium carbide has its own diffusion coefficient compared to hydrogen going through niobium carbide. Hydrogen loves to wiggle into spaces, and at certain temperatures more than others, at certain velocities more than others. It's very, very dependent on the situation. But I was able to find some diffusion coefficients for a few of the materials with the hydrogen. And ultimately, this is the parameter we set up to be able to compare. This is all of the base data, and sigmas are just errors. Figured it'd be useful for anyone interested in that. But these are all of the coating that we looked at. And the main thing we first tested with this is that row in the third column is called the reactivity. It's essentially like a derivative telling us the trend of the reactivity. So is it going up? Is it going down? If that maximum reactivity is negative, that means there will not be a nuclear reaction. Therefore, we had to exclude anything negative in the row max. But we also needed to consider anytime it was positive in the least reactivity. That means that it would continue to sustain a reaction no matter what we did, which is highly dangerous. That is not something we can actually work with at all. We need something that will be on when we want it on and off when we want it off. Therefore, only positive in row max and negative in row min were considered going forward. And then we had these materials left. Now, as I said, we couldn't find diffusion coefficients for a lot of them. So I also put the parameter of that, the comparative parameter divided by the diffusion coefficient and compared those. And this is in order, and we found from the experiments zirconium carbide did behave significantly better than niobium carbide. So this all makes sense and goes with that. But we also have to remember that weighting those different pieces of the parameter could be exceptionally useful in future comparisons. But the molybdenum 92 is the one that really stuck out because that's been actually very popular. And very important here is that a lot of these materials have a number of isotopes, and some of them are very friendly or completely neutral to neutrons, but some of them will absorb them and make reactions harder. That's why I put molybdenum 92 there, is because if you enrich out all of the isotopes that really are not helpful and leave it at the one that's really nice, 92, you get a good job. As opposed to molybdenum as it is about halfway down the table. But this is simply a basis for what future experiments and studies would be useful for other coatings. Now, the bimodal work, which is honestly what I'm the most excited about, is inserting a heat pipe, which actually my dissertation project ended up being a heat pipe model that will be able to help analyze this better, because we have the tools to be able to thermally and neutronically model these reactors. But heat pipes are kind of a magical system. To be two-phase flow in a confined pipe is very difficult to model, especially because it ends up being turbulent and all sorts of fun things. Fun. But putting these in the reactors is so incredibly useful because, if only because, they are not connected to each other like most other fluid flow heat transfer systems are. So one of them breaking does not remove the system. And that is a huge deal. However, this is a very new concept to be able to do this, especially in a nuclear reactor, or a nuclear thermal propulsion rocket, I'm sorry. But we have nuclear electric propulsion as well, where instead of the NTPs that I'm talking about here, they instead generate that heat using coolant, convert it to electricity, and then use that electricity for microthrust. And those are extremely useful for purposes like being able to supply electricity on board. And that's why these bimodal reactors came about, is because not having to worry about efficiency when you're doing thrust is a big deal. It's pretty nice. So this bimodal system, there are designs in which you can run one or the other, that they have a xenon loop that you can do that or the hydrogen. And this is the first one that you could run both simultaneously. And that is a big deal because then we could have onboard electricity at the same time as thrust and not have to have other systems. We could have it very simple. And this particular design, I chose a lithium heat pipe based on a very thorough experiment by Dr. Merrigan. And he used a mostly molybdenum, and we just talked about how great that material is, shell and wick to move the heat, to sustain the heat pipe. And that green section in the diagram is the shell itself. And the blue, orange, and blue are parts of the heat pipe. You can see the lithium and the sections there. I also ended up adding an adiabatic sleeve. I have a bunch of names for it: semi-insulating, moderating, adiabatic, semi-sleeve. Basically, it would not go all the way up. If this was the entire reactor, it would probably come to about here. And the reason is because when we looked at all these materials, the hydrides have an extremely low melting temperature, but they are extremely good at moderating, and they are just all around useful. So the inclusion of them, after investigating how a single heat pipe would function because it's replacing a huge moderator element, we found that the zirconium carbide, the best one in the previous analysis, was getting a negative reactivity at its max. Showing there is the max, the bimodal and electric only. And that obviously won't work. No nuclear reaction, no propulsion, no electricity. But the hydrides that we excluded for having that positive minimum reactivity, they worked pretty well here. They had negative minimum and they had positive in both configurations. The two configurations we tested were a bimodal, in which we just assessed them both, and an electric only to see what would happen if there wasn't the hydrogen, which is also a very good moderator, in the channels. And it performed, it succeeded. Unfortunately, because of this, their very, very low melting temperature, you can't just put them along the entire length of the heat pipe. What we would have to do is put them only at the low temperature end of the the low temperature end of the heat pipe and reactor, because it ranges from 100 Kelvin to 2500 Kelvin. And we would have to do different coating, maybe multiple, maybe just one, at the intersection. And this could also help with the midband region by putting a coating that is more useful at that midband region. But what we found here is that with that moderating sleeve and with all of the other features we did, like we took the lithium and we took out some poison isotopes. We took out the poison isotopes of the molybdenum, and it worked. So the next step was, how much can heat pipes actually remove? This reactor at its normal operation generates 563 megawatts, and based on the experiment, those heat pipes, that geometry, everything else, can remove 68.9 kilowatts, which is substantially less, but a non-negligible amount of power. It would definitely give you basically what you need on a spacecraft. Now, I mean, that depends on if you're doing any like weird experiments, but for a lot of basic features, yeah, that'll definitely serve your purpose. And even if you consider the efficiency losses, you've still got plenty of power coming in. This is worth consideration. However, if we wanted to run at only this electric mode and turn off the thrusting, because a lot of these missions, you actually only use the propulsion mode for about 2 hours across the entire mission, even to Mars. So we would need to have an ability to make this reactor operate at only outputting about 70 kilowatts. And that is something that we can do. We can just create a new design. And this is not designing a bimodal reactor. This is simply trying to see whether there is potential for a bimodal reactor of this nature, of this highly enriched uranium, graphite matrix, PeeWee variant reactor. And there is. It's something that a graduate student was able to do in her spare time because I love this. And so I'm excited to see what professionals, hopefully me in the future, would be able to do with the tools and time to create a real design for this. It's just very exciting that we could get to Mars faster, we could get to all the asteroids. It'd be great. And lots of references. And that is my presentation. I'm happy to accept any questions.
So folks, any question, please, you can raise hand or type in Q&A. Well, I do actually have a quick question. What's the thickness of those coating you are talking about?
Oh, the thickness is incredibly small. I had it. It is, let's see. Believe it was on the order of micrometers.
Micrometer. So what's the mechanism? How do you apply those coating?
It's diffusion coating. They sort of just spray it.
Oh.
Yeah, so they spray it down.
And cure it. Okay.
The mechanism for it is so crazy because you're spraying it down this teeny set of holes. And it's wow.
I see.
It's actually a very large machine. So I've seen it. I haven't seen it in action because these have not been made in a while. But it's very interesting.
Well, I think there's a Q&A, but it's basically asking about the slides, and it was commenting it's an outstanding presentation. I don't know if you can see it. It's a Q&A box.
Let's see if I can try.
Yeah. But in the meanwhile, I think the diffusion you are talking about is more like a Arrhenius type diffusion, right? It's for the hydrogen to pass through the coating. Okay, so
yes, it's trying to inhibit that. Basically, it's the goal is to inhibit it from actually passing through, whether as a sacrifice or whether as a real deterrent is pretty acceptable either way, from what I've heard.
Yeah, and if you do this diffusion coating and also you see the zirconium, then there is also the issue of kind of structure, in this coating, and how much is the the nitrogen and the phase, of the coating material inside. That might also affect the way how they behave in the diffusion process.
Absolutely.
And I think, of course, the major issue, people are so excited about advanced propulsion. Actually, last week, we have a speaker from Texas. It's called the Limitless Space Institute. So they were doing some kind of advanced propulsion design contest. Just basic, the question for you is, what did you think? What is the time frame? You think this technology can kick in, that you think maybe SpaceX or some company will be interested, to do some tests, to use it to go to Mars?
So that is a very interesting question, and I'll start with what people are currently doing. I know that NASA's MSFC, is working on a different kind of fuel element. They're trying to do a low enriched uranium because it has easier safeguards. It's pretty useful in that way. There's a whole debate that is probably easily an hour-long presentation just about whether low enriched or high enriched uranium is the way to go with this. Suffice it to say, there are benefits and drawbacks to both. but they are basically testing individual fuel elements right now using depleted uranium, that sort of thing. So there are no real nuclear factors. They just heat it up and see how it does. We really can't do too many nuclear tests. It's pretty hard. The closest we've had lately has been the Krusty experiment, which Los Alamos National Laboratory actually did about 2 years ago, I think. And what it was is just a very simple reactor and nothing like this. It had just like an oatmeal container sized reactor that had heat pipes, took the heat, converted it. Super simple. And they just ran it out at the Nevada test site. It performed exceptionally well. They were able to actually evaluate it super well, and that hopefully paved the way to have more nuclear experiments. But right now we're on such a smaller scale that testing this would be very difficult, especially in the government sector. In the industry sector, doing pieces much like NASA is doing, where you are testing how it responds to the heat, because that's basically what we're playing with in a reactor, is a very good first step. BWXT was working very hard on these reactor rockets, as well as a number of other nuclear companies. I'm familiar with aerospace companies dabbling a little bit in it, but it tended to be a good idea to work with a nuclear company because reactor design can be really hard. And that's why I started with somebody else's design and played with individual pieces of it to see, can we improve one piece at a time? And that's how a lot of this stuff works. That's why this would be a collaboration, highly. And that's why I chose the field I did. The multi-physics intersection between aerospace and nuclear is not commonly held within a single person. And being able to communicate between the two effectively is a goal of mine, especially in this avenue, because I started out more in the aerospace side and learned nuclear to be able to facilitate that communication of it. I see a very bright future for this. A lot of people talk about the really, really amazing things like EM drives, and I'd love to see it, but a lot of those are more for even longer missions than Mars because they're microthrust based. This is a lot like a chemical rocket, just a bit bigger in terms of ISP. But it actually kind of caps out on its utility a little beyond Mars. So you actually do definitely want those next level. This to me is a stepping stone, and it's one that we have to take to be able to get to those next advanced reactors. It's something that will take us to that intermediate zone where people are very worried about what a transit to Mars would look like for humans particularly. But this would reduce the time, and it would have a more robust onboard power system. It's something that we have the means to build. It's something that we need to work harder to be able to test effectively and safely. But it's something that a lot of people really are interested in their own ways. Like, I like nuclear thermal propulsion. Some of my bosses love nuclear electric propulsion, and it's a fun little lunchtime debate we have. But it'll ultimately be decided by the mission. When NASA comes and says, we want this, we'll be able to say, this one will do it best.
Excellent. Yeah, very smart, intelligent. That's the right choice. And Las Vegas and Los Alamos is certainly a very important site. I was in Las Vegas with Marty. You know, Marty in the So we know that's very important for nuclear test site, the nuclear engineering very strong in that area. Very keep the good work. And I think there are a couple of questions. Can you see the Q&A?
For some reason, I only have the thumbnails showing.
Okay, don't worry. Let me do this. I think the first two questions was from Dr. Bragg. He was asking about the slide. Would you be able to provide a link to your slide? So we can either post it for you, or you can forward to to the Dr. Bragg directly. Whichever way that we can do it for you. Yeah, and he was saying is this is a great, outstanding presentation. Yeah.
Well, thank you.
And there is a question from Rio. He was saying, how would the heat from the bimodal reactor be used to power the electrical system on board a theoretical ship? And would you envision a configuration of conventional reactor, or would this be something that would need more time to develop?
That is an excellent question. I'm going to start with how this would power. So let's go back to heat pipes. Can everyone see the slides okay? Are these showing?
Yes, yes.
Great. So the heat pipe shown here, how this would work is that the reactor would be surrounding this evaporator region. And the adiabatic is just if we need to move it away from the reactor at all for any reason. And in this case, how I've visualized it a lot, and a number of people have presented their designs, is that for radiation safety, the reactor tends to be offset from the crew cabin by as much as possible. And so it's generally that, I'm going to put this back down. You would have sort of, let's try it this way. You would have something resembling like if this is the entire cabin, crew capsule, etc., you would have your crew try and remain in this region, and this be supplies and your hydrogen tanks, oxygen tanks, water tanks, whatever else you're bringing, just supplies. And then you, some designs have it right after where the reactor would be. Some of them have it offset a little bit, but essentially you would have a little bit of shielding there in the way, and it would be that far off. But and so any amount of that space would be the adiabatic region, but you have a power conversion unit probably right around this region or wherever in the cabin is, depending on how your tank configuration is. And at that point, you would have whatever effective power conversion system you would want based on the temperature you're getting. Because I don't actually have temperature measurements at the moment for what sort of outputs we would get, because it depends on how far it's going. Like if you're traveling almost immediately out of the reactor, you're going to have basically the same temperature that was put into the heat pipe. But the further you go, the more temperature you'll lose, at least a little. And so whatever temperature we're getting out will definitely dictate what power conversion system we use. And then you get your electricity. I'm not sure if that answered the question. I'm not quite as much on the thermodynamic side as the heat transfer side. It's something that a lot of other people have looked into, the more complete design of what this entire system would look like. And as such, some of these designs actually have 3 of these reactors on them, but they have a smaller version of it. This one produces 25,000 pounds of thrust, but there's a version that produces, I believe, 6,400. And that one is the baseline version of this SNRE, because this is called the, let me find it. I believe it is the axial growth engine. So it's actually longer. But there is a shorter version that is actually the size of the Pee-wee engine. It's 81 centimeters rather than 132. And that one, they put a configuration of 3. This one, I believe they've said it's viable to do a single, but it really depends on your mission, whether you want redundancy. A lot of us love to have our redundancy, where if we lose one, we'll still be okay. So having that configuration of 3 can be ideal in that way. But it really depends, because there is also the factor of how do you layer for redundancy, because if you have them like this, and you lose like that one, then suddenly your rocket's going to be weird. It's a lot of questions that are almost always just mission specific. Basically, the more information and generalizable options we can provide, the more likely we'll be able to succeed ultimately when the question is asked, can you make this happen?
Yeah, I think the question, the person Rio is unmuted. So Rio, do you want to say if this satisfy your question? Does that answer your question, Rio?
It's actually Roel, but yes, it answers my question thoroughly. Thank you very much. Appreciate it.
Happy. Glad to answer any questions. This is fun.
Yeah, then we have a question from Mr. James Robinson, and you are unmuted. So Mr. Robinson, you are welcome to speak out your question.
Thank you. Yeah, I was wondering if you had any thoughts on Dumbo-style reactors, the NTRs that have kind of a radial flow path, and if you had any, if you comment on any of the challenges of those.
I have not heard of those. I'll have to look into them. Does that mean that it's sort of a polar type radial path, or that it moves outward?
The documents I've seen show it traveling outwards through the fuel elements. They're really interesting.
Does that have to do with any molten salts?
No, it's solid. Not that I know of. It's solid core still.
I have never heard of those. I've just taken a note. I'm going to be looking into them. Thank you. I'm sorry I
Sure.
can't give a perspective on it.
No, thank you.
I think originally Mr. Bob Caplow has a question, but he said that you all actually just answered his question. Bob, is that true? Bob, do you want to say something?
Yes, I was going to ask what kind of thrust these things produce, and I see it on the slide you just rolled back to. So 25,000 pounds is significant.
Oh, yes. These are big boys.
And I was comparing it to some of the ion engines used on some of the asteroid spacecraft that are very low thrust.
And that's one of the key features of this particular design is it more closely resembles the chemical rockets in that way, where it's a lot of initial thrust and then you need a lot of slowdown thrust, but you actually aren't operating it for very long. In a Mars mission, it is about 2 hours that it would be running.
And actually, that also makes me wonder that you could get to Mars a lot faster if you spent half the trip thrusting and then turn around and spend the other half of the thrusting backwards to slow down.
Exactly.
Reach much higher velocities on the way.
Yep. That's a parametric study that has been pretty popular is what is the correct amount of thrust to slow down and when should it happen? It's a lot of people tend to just put a chunk at the beginning and a chunk at the end, if only for proof of design.
Thank you.
Oh, and so there are other basically advanced reactors beyond this one, and including nuclear electric propulsion are more like that ion one where they have the micro thrust that you just continue operating it throughout the entire mission, and you would do it forward for the first half and backward for the second half. And one of the benefits is reduced G-forces on the crew, but you're going really slow at first. So that sort of thing is very useful for a longer mission. That's why we tend to think of the nuclear thermal propulsion rockets as being Mars and asteroid belt type mission areas, and the advanced reactors or advanced propulsion that are more on the micro thrust scale are better for a little longer, any amount longer.
Yeah, and actually a few years ago, I was in the AIAA Space Conference. I think there was a talk exactly. They were not proposing which type of nuclear engine, but they were actually proposing what you were saying, use a short trip. This also reduced the radiation, microgravity exposure. So this is one of the answer to that. And I can tell actually we actually have AIAA member or people, company working on some type of nuclear, engine, but which we cannot disclose. Then of course there are people working on the radiothermal isotope, those just for the rover missions. So there are a lot of people that are very interested in this kind of thing you are doing. So keep the great work, and we have also newsletters, and whenever you are ready to give another talk, and we can post a news, your article, just let us know. Let me know. We'll be happy to do it anytime.
And anyone, please feel free to contact me. The paper that corresponds to this particular presentation was released for the International Astronautical Congress, but if anyone's interested, I am happy to provide it.
Yeah. Please send me the link, and then I will be because after the event we have the article or screen, some kind of words for the event. We can post it there as well.
Sounds great. Yes, and anybody who wants the presentation as well, any questions or anything, I believe my email might have been listed on the.
Oh, you want? We can post it. Yeah, we can post it.
I'm always happy to answer questions on this.
No, typically we for privacy reason we don't post it in the first place. But if the speaker feel okay, that's okay.
Yeah, it's fine with me.
Okay, thank you. So if I don't see any. If no further questions, so let's thank Valerie for the great presentation. Great job, well done. Best wish for you. Keep the great work, and look forward to hear from you soon next time.
Well, thank you so much.
Yeah, great pleasure. Anytime.
It's always great to be here, and always great to work with you guys. Have a
Good. Thank you. Good. Thank you. Great pleasure. Always. There's a question coming up.
Ooh,
Yeah, outstanding work from Dr. Black.
thank you.
Excellent.
I can't wait until my heat pipe model is done and then really analyze this stuff.
Yeah, that's definitely. We'll have another event and an article about your progress.
And by then I'll be Dr. Lawdensky.